Welcome back to our discussion of muscle cell physiology. So I want to do, before we get into the details of this particular video, what I want to do is I want to go back and do a quick recap just so that we make sure we're all on the same page here. So these proteins right here, just so you're aware of this is what we call, this is the voltage-gated sodium channels that we talked about in the previous video. And what we talked about were, if this is the muscle cell membrane, so this right here, this is the muscle, essentially it's the sarcolemma, right? That's what we call the muscle cell membrane. In here is the cytosol, out here is the extracellular fluid. These are the voltage-gated sodium channels. And we talked about how essentially what the action potential that goes along the muscle cell membrane is its influx of sodium ions, right? So what I'm going to do is I'm going to do a really quick recap of what we talked about. So I think by this point, if you watched the previous video, you understand that these voltage-gated sodium channels, their subunit 4 is referred to as a voltage sensor. Okay, and the voltage sensor itself is very sensitive to positive charge, essentially. Okay, so in other words, if I start building up positive charge inside the cell, that voltage sensor, which faces the cytosolic side, is going to sense that change in charge across the membrane, and the protein's going to change conformation. And if you need more detail on that, I recommend you go watch the previous video, but we're just going to do some very general physiology here. So basically, I have all this sodium coming in through opening of previous voltage-gated sodium channels, and so I think you have the intuition that there's going to be a bunch of sodium that starts accumulating here. Well, that means I am essentially building up lots of positive character here on the inside of the cell if there's lots of sodium influx. And so this voltage sensor on the voltage-gated sodium channel is going to sense that. And so what's going to happen is you're going to get influx of sodium. So what happens essentially is that voltage sensor senses the positive charge that's entering the cell, and in that vicinity, that particular voltage-gated sodium channel opens and allows sodium through. And then you can imagine that voltage-gated sodium channel is going to remain open for a while, and you're going to start building up more positive charge in this vicinity around this particular voltage-gated sodium channel, right? So you're building up positive character there, and once again, the voltage sensor that I have there in black, the voltage sensor is going to sense that as well. And so I think you have the intuition that now, once the voltage sensor senses it as that positive character building up in that vicinity, then it's going to change conformation and allow sodium through this one. Right? And then you're going to allow sodium through like this and so forth, and then you build up all this positive character around that voltage sensor on the next voltage-gated sodium channel, right? And so it's going to change conformation, and that's going to allow the next sodium through. It's going to open that channel, and then you're going to build up more sodium right here, more positive charge, more positive character. This voltage sensor on subunit 4 of this voltage-gated sodium channel is going to sense that, and then it's going to change conformation and open the channel, and more sodium is going to come in. And this process, I don't think I need to keep doing it, is basically going to be propagated along the sarcolemma, along the muscle cell membrane. And this is the basis of the muscle cell action potential that propagates along the sarcolemma. So hopefully this makes a little bit of sense. And I tried to drive home in the last video that the actual propagation of the action potential is done by sodium influx. But what I said at the very beginning of the video was something that we're going to cover here, is that sodium is not the only player in this action potential. That even though sodium influx drives the action potential, there is some interplay with potassium. And so that brings us to this figure. And the first one over here has to do with the actual neuron. This is going to be saved for 2 weeks from now. We'll talk about the axon action potential. In this case, we're just going to be talking about the skeletal muscle action potential that's propagating along the muscle cell membrane. So what you'll notice is that, in a neuron, the resting membrane potential is about -70, and you can see that at rest, the resting membrane potential changes a little bit. We're not really so much concerned about numerically what the resting membrane potential is. I don't really care so much about that. What I care about is analyzing this figure, analyzing the graph to see exactly what happens. Well, here's the idea. I'm starting with something that's very negative right here, and this is with respect to the inside of the cell. Okay, so let's kind of draw a hypothetical cell right here. And let's go ahead and draw our voltage-gated sodium channels. Well, if I start out at rest, so this right here, this is at rest. If I start out at rest, that means I'm not influxing anything to any great extent. But as soon as I get the signal to open those voltage-gated sodium channels, what's going to happen? Well, if this is my extracellular fluid, sodium's then going to, the voltage sensor is going to sense some change in charge, and then I'm going to get sodium influx here. Well, what's going to happen is the inside of the cell is going to get more positive in general. Okay, so what's going to happen is, like you can see, the voltage is becoming more positive. So as I go this direction on the curve, right, the inside of the cell is getting more positive in that vicinity, right? But here's what happens where we deviate from the last video a little bit. We talked only about sodium, but there's another player here as well. And I'm going to kind of draw it in here, around right here, because this is usually where it starts to become important. This particular type of channel that opens is called a voltage-gated potassium channel. Okay, and I made a little aside to that at the very beginning of the previous video. Is that over here, right in this area right here, this is essentially where you start to get what we call voltage-gated sodium channels open. Okay, but the thing is, as we'll talk about in a few minutes, there comes a point in time when you get a certain positive character inside the cell, a certain amount of positive charge, that it actually triggers the opening of the voltage-gated potassium channels. Okay, so this is around the time when the voltage-gated potassium channels open, and they do it at a certain voltage that exists inside the cell once you start building up the positive charge. Okay, so you're going to have these voltage-gated potassium channels around this time, sort of in the middle of the curve that open around here, and then you're going to get to this point at the top. This point at the top is really important, because at this point, notice that when I start going down this side of the curve, what's happening? Well, when I start going down that side, I'm getting more negative inside the cell. Okay, so that's because at this point, okay, think back to our voltage-gated sodium channels, what has to happen is the voltage-gated sodium channels, they close and they inactivate. Okay, there's mechanisms by which the voltage-gated sodium channels inactivate. And so that means that they're in what's referred to as a refractory period and they cannot open. So those guys are closed. Okay, I forgot the E there. They are closed. Okay, and at this point they're inactivated. Okay, but the other thing is that at this point what we essentially have are these voltage-gated potassium channels. They are open. Okay, at this point. And so what you have continually is you have this potassium influx, right? Around this time you have, let me draw it as a K, that's the symbol for potassium. So I have potassium, it's efflux, because potassium is essentially going to move the opposite direction. So if this is my potassium channel, potassium is going to start out inside the cell and it's going to move outside. Okay, so what I'm essentially doing by that is instead of moving positive charge inside the cell, I'm actually moving it out of the cell, from the inside to the outside. And that's why you see the membrane potential actually becoming more negative. So notice as I'm going down on this curve, right here I might have been at positive 30, now at this point I'm approximately at maybe like negative 35 or negative 40 or something. Okay. Now at this point, and again, we're not being rigorously exact with this, but sometime around this point on the curve, something else happens. Okay, and it has to do with the voltage-gated potassium channels. Okay, the voltage-gated potassium channels, they start to close, and I'm gonna say this because it's really important. They start to close. Okay, the thing about voltage-gated potassium channels is they're really not very good at closing. So they essentially remain activated for a lot longer than the voltage-gated sodium channels do. And so what happens is you see this kind of shallowing of the curve right here. Instead of having a really sharp a sharp movement downwards on the curve, you see this kind of shallowing out because the voltage-gated potassium channels don't close as well. And so what you see is, in fact, if you're looking at this mathematically, the derivative is actually pretty shallow. Okay? So let's kind of do a regroup here. So initially what happens is, as we saw before in the last video, the action potential is initiated by positive charge moving inside the cell, and so our voltage-gated sodium channels open. Okay? That's one key thing to understand. Then what happens is the positive charge keeps moving inside the cell, and as you get more and more positive inside the cell, you get to a really, really high positive threshold, and then the voltage-gated potassium channels open. And they're going to open a lot more slowly, and so eventually you'll get to this point up here where voltage-gated sodium channels close and activate, but the voltage-gated potassium channels remain open. And then what's going to happen, I think you have the intuition, if the voltage-gated sodium channels are closed, you're no longer putting positive charge into the cell, but you're still taking positive charge and moving it out of the cell, right? And so now the inside of the cell is becoming more negative, and eventually it's going to get back down to the starting point, which is right there. That's the starting point. Okay? One important thing to realize is this part of the curve right here. This is called the net depolarization. On this side where you're returning back to resting membrane threshold, this is called the repolarization. Okay? So essentially what you can say is that the depolarization is initiated by the sodium influx, and the repolarization is initiated by the potassium efflux. So hopefully that makes a little bit of sense. But now we're going to kind of delve into it a little bit. So in the last video we talked about voltage-gated calcium channels, and we talked about voltage-gated sodium channels. What we're going to find is that there's another type of channel that's also very similar, and it's what's referred to as the voltage-gated potassium channels. Why is it similar? Because they are also voltage sensitive. I think in the last video we talked about how these two have a subunit 4, very similar to the voltage-gated sodium and calcium channels, that is voltage sensitive. But there's a very important difference between the voltage-gated sodium channels and the voltage-gated potassium channels. Okay? The thing is for voltage-gated potassium channels, it takes a much higher positive charge inside the cell to initiate these channels opening. Okay, so they're very picky. They're not just going to open in response to a little bit of positive charge. No, they take a lot of positive charge to open. Okay, so here's the key point. Thus, before voltage-gated potassium channels open, the inside of the cell must become extremely positive with respect to resting conditions. So it has to become really positive for them to open, much more positive than it takes for the voltage-gated sodium channels to open. So as a result of this, the voltage-gated potassium channels will always open after the voltage-gated sodium channels during the action potential along the muscle cell membrane. And this is very similar to what we saw in the previous couple pictures in the previous lecture. We see the subunit 4 is voltage sensitive, but instead of what's happening in the other videos where we saw sodium influx, in this case we're going to essentially see when this activates, potassium is going to efflux. Okay, so going back to what we talked about earlier, we said depolarizations occur by moving sodium down its concentration gradient from the extracellular fluid to the muscle cell cytosol through voltage-gated sodium channels. That's the propagation of the action potential. Okay? Thus, as time progresses, the inside of the cell in regions of depolarization becomes much more positive. Okay? And when I say much more positive, I mean very positive. Okay? This new extremely high positive voltage is sensed by the voltage-gated potassium channels. Okay? And they are similar to other channels in the sense that they too sense voltage, like we said. Okay? The difference here is that they are having a much higher they have a much higher threshold for positive charge, meaning, remember what I said, they're much pickier. Okay? They're not just going to open in response to a little bit of positive charge. They're going to take quite a bit of positive charge to open. Okay? which means that, like I said, the voltage-gated potassium channels in that vicinity will always open after the voltage-gated sodium channels. Okay? So when this much higher voltage is reached, the voltage-gated potassium channels activate, channels open, and potassium diffuses from the inside of the cell into the ECF down its concentration gradient, meaning the term we use for that is it effluxes. It effluxes. So here's the kind of the general ideas. The positive charge migration is in the reverse direction than we saw in sodium influx, because we're effluxing the sodium. Okay, so if potassium is effluxing, kind of go back to this slide right here. If potassium is effluxing on the repolarization part of this curve, right, we're moving positive charge from the inside to the outside. And that's why you see the voltage become more negative. Because if we're losing positive, that means we're gaining negativity. And so eventually we're going to get back down to this point, which we said was the start voltage. Okay? What we're actually going to see in the next video is that we're going to have to use something referred to as a sodium-potassium pump to get the ions back where they belong. Because if you think about it, I have all this sodium inside the cell now, and I have all this potassium outside the cell, but that's not where they actually belong at rest. So I'm going to have to do a little bit of work to essentially get the ions back where they belong. But hopefully that makes a little bit of sense. So now what I want to do is I want to kind of give you a pictorial reference of what's happening. Okay, so each one of these things, I want to make this perfectly clear. This is one point in space right here. Okay, this is just one area of the muscle cell membrane. And this area that I'm boxing, all these areas are the same point. Okay, what I'm doing is I'm just showing you the same point at different points in time. Okay, so let's say that these are all the same point. All the same point in space. All the same point in space, but let's say this is, say, at time equals 1. I'm just saying arbitrary units. This is at time equals 2. This is at time equals 3. This is at time equals 4. And let's say this is time equals 5. Okay, so I want to make this perfectly clear for your understanding. Okay, these are all the same point in space, but they're at different points in time. Okay, so in other words, this channel right here, remember the blue is the voltage-gated sodium channel. This is the voltage-gated potassium channel. Okay, this one I'll designate this as A. This is B. This is the same protein, right? The exact same molecule. I'm just talking about these points in space at different regions in time. So hopefully that makes a little bit of sense to you. So here's kind of what happens. Remember how each of these guys has a voltage sensor? All the voltage-gated sodium channels have a voltage sensor. But remember how voltage-gated potassium channels have a much higher threshold? I'm going to denote that with a much larger voltage sensor. So these guys all have a smaller voltage sensor, right? Okay, and the voltage-gated potassium channels is much larger because they're sensitive to a much higher threshold of positive charge. Okay, so hopefully that makes a little bit of sense to you. So here's kind of a time coordinate of what's happening here. Well, initially what's going to happen is I'm going to have, a little bit of positive charge that accumulates here in the area of the voltage-gated sodium channels. And what's that going to do? Well, as we said before, when I build up this positive character here, that's going to initiate these channels to open, and sodium is going to influx here. Okay? Well, if sodium influxes here, now I have a little bit more positive charge, right? I'm denoting the amount of positive charge by essentially the number of these positive circles that I have. Okay, so hopefully that makes a little bit of sense. And in this case, maybe these voltage-gated potassium channels, maybe it's not enough positive charge for them to open. But, the sodium ions, they continue to move through, right? So now I have 3 of these positive charges. Again, I'm just denoting the amount of positive charges I have by the circles with the positive, right? So now I have even more positive charge. But let's say maybe at this point, now I have all this positive in here. Maybe, for example, this is the threshold for the voltage-gated potassium channels. So what's essentially going to happen is I'll still have, for a moment, I'll still have sodium that comes through here, but what's going to happen now is these channels are going to open in potassium effluxes. Okay? So at some region in time on that curve that I showed you, there's going to be sodium influx and potassium efflux. So if we go back to the curve, that kind of region in space, I'll do it in let's do it in yellow. That region of space kind of corresponds to that area right there that I highlighted in yellow. That's where the the sodium channels are still open, but the potassium channels have become open as well. And so you're actually getting migration in both directions. Well, then let's say we do get to that point at the top of the curve, right? Well, at that point, I think you have the intuition that the sodium channels close, right? The sodium channels close, so these guys are closed at this point, okay? But the potassium channels are open. So now potassium, right? Potassium is going to efflux, right? And so then maybe at that point, maybe instead of having these 3 positives, I'm back to 2, right? And then let's say potassium continues to efflux, right? So potassium continues to efflux, right? And then maybe that brings me back down to the initial 1 positive that I started with. Okay, so let's kind of think about what this means at points in time, basically. So at the first point in time, there was a little bit of positive charge right here that maybe caused the voltage-gated sodium channels to open. Okay. So sodium influxed in because the channel opened. Then I build up, I build up a little more positive charge right here. So I build up a little more positive, but it's still not at the threshold that opens the voltage-gated potassium channels. But the sodium channel remains open and sodium influxes. Then let's say sodium influxes, and so now I have all this positive charge. But let's say that reaches the threshold by which the voltage-gated potassium channels open. So the potassium channel opens and potassium effluxes. Okay? So then what happens is, you'll have this situation where sodium is influxing, potassium's effluxing. Remember, that corresponded to this yellow part of the curve right there, right? And then we get to a point where the voltage is essentially so high, it's so positive, that these voltage-gated sodium channels turn off. That's why I X'd it out. They turn off. Okay? But what happens is the voltage-gated potassium channels, they're still open. So potassium continues to efflux. So I went from maybe 3 of these positive guys to maybe 2. Again, it's just very abstract, very arbitrary, but notice that the positive charge is now decreasing because I'm moving potassium out. Okay? And I go to 1 more unit of time later, and again, these sodium channels are still closed, but now potassium's effluxing, but I'm still losing positivity inside the cell because I'm moving positive charge out. Okay, and I want to show you kind of the net effect of what this looks like. Okay, so let's take the same point in space at the very end. So maybe this is the very end right here. Maybe t equals 6 or something like that. Okay. So now my situation is this. I have all these sodiums in here. Let's say this is the extracellular side out here. This is the intracellular side, the cytosol. So I have all these sodiums in here. Why are they in here? Well, because the sodium was influxed in. The voltage-gated sodium channels open and it diffused down its concentration gradient. Well, I also effluxed a lot of potassium, right? So the potassium's also out there in the extracellular fluid. Okay. Here's the problem, though. So if I go back to this curve, okay, I have the resting membrane potential restored, right, approximately. The problem, though, is that now these ions are in the wrong place, okay? So wouldn't it be nice if I could take this sodium and move it out there, right? And wouldn't it also be nice if I could take a potassium and move it back here? Because that's essentially where they belong at rest. Well, it turns out that in the next video, what we're actually going to do is we're actually going to look to see exactly how that happens. And it's done by an enzyme referred to as the sodium-potassium ATPase, which is also referred to as the sodium-potassium pump. Okay? But before we go into that, I want to at least look at one more time kind of what's happening here now that you've seen this little schematic. So back to this picture right here. So remember what's happening here is at this point the voltage-gated sodium channels open. Voltage-gated sodium channels, they open. And then you start what's referred to as the depolarization phase. Okay? So we're going along this curve, and eventually we're going to get to a point at which, and remember they do it really slowly, but we're going to get to a point at which the voltage-gated potassium channels open. And then we also have the voltage-gated sodium channels still open. So voltage-gated sodium channels, they are still open at this point. Then I'm going to get to a point at the top. I'm going to get to a point at the top where I say voltage-gated potassium channels, they're open, right? But voltage-gated sodium channels are closed. Where does that correspond to in this picture? Well, it corresponds kind of in this region right here, between here and here, right? What happened? Well, I was initially having the sodium channels open, potassium channels were open, but then the sodium channels closed because we got to a certain voltage right here that caused their inactivation. So now the sodium channels are closed and inactivated, but the potassium channels are still open. Okay, so here the voltage gated, this got erased, potassium channels are open, and now I'm traversing this area of the curve right here. And approximately I get to maybe about this point right here. We say the voltage gated potassium channels, keyword is begin to close. Not all of them close at that moment, but they start to at least, and that's why you don't see this sharp movement of the repolarization down. It kind of levels off very slowly. So this phase over here is called the repolarization. And this right here, this is the action potential for the skeletal muscle. Okay? And you'll find, I think, that it's going to be very similar to the motor neuron action potential that we'll talk about in another week's lesson. Okay, but hopefully this made a little bit of sense to you. Just keep in mind all of these systems, these voltage-gated channels, are going to work almost identically. They all have a voltage sensor. The key difference for this video is just that the voltage-gated sodium channels, they don't require as high of a voltage. They don't require as much of a positive charge inside the cell to open, whereas the voltage-gated potassium channels require a far higher positive character inside the cell, meaning they're pickier. And so always, 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 the voltage-gated potassium channels will open after the sodium channels, okay? Potassium channels open after the sodium channels. And hopefully by seeing this little picture right here, this little time schematic, you do see that the sodium channels open, you start to build up positive charge, but you get to a point at which this positive charge triggers the opening of the potassium channels, then the sodium channels inactivate while the potassium channels remain open, and at this point, at the very end, right here, you're kind of in a little bit of a pickle here. Because now your sodiums are on the inside of the cell, your potassiums are on the outside of the cell, and you've got to do something to fix that. And for that, you're going to use the sodium-potassium ATPase, or the sodium-potassium pump. We'll look at that in the next video. See you there.